Good morning. Is anyone there? Shailaja. Who's Shailaja? Yes, ma'am. So I think all of the members came, or I don't know. Shall we start? Every members came. I can't see. No, wait. Okay, 6 participants.
Ma'am, we'll just wait for 2 minutes. Others will be joining.
Sure.
Okay.
Sure.
Students, any idea if others are also joining? Hamsini?
So I'm not sure. I just came home from school.
Okay. So your school, did it get late? I believe it is still 4, right?
Yeah, it is actually till 4, sir. It got late. My parent picked up me late.
Okay. That's fine. Okay, that's fine. Okay. So anyways, good evening, students. Are you able to hear me? Everyone?
Yes,
sir.
Okay. So just wanted to give few updates. One thing is I got the schedule of your school recently only. This week I got a schedule due to which we need to work upon more number of classes. I believe few chapters are pending from our side. So to ensure those things are balanced well, today we have requested Aishwarya ma'am to take class. I think she has started S block elements a month back, right? So which is a part of your term 2 syllabus. So today and tomorrow, she'll be taking 4 hours of class on S block elements so that is over. During the coming week, what we will do is we'll plan for a few more extra sessions in chemistry so that we are able to complete the remaining 2 chapters, that is equilibrium and the P block elements as well. So there will be a parallel teaching that will be going on. So one sir will be like Akash sir will be taking care of physical chemistry and ma'am will be taking care of inorganic chemistry. Is that clear, guys? So I hope everybody is able to understand. So today and tomorrow you'll have S block elements. So there'll be a small recap which she has already taught, maybe for the first 10 to 15 minutes. I suggest everyone to have discussion with her. Okay, try to have good interaction, and you have any doubts, get it clarified. So now she will take care of the remaining class. Ma'am, I think we can get started.
Okay, sir. Okay.
Yeah.
Sir, is the board and the PPT is visible?
No, ma'am, I think the screen share is not on. Well, I'm not sure. Oh, yeah, it is visible. Sorry, my mistake. Yeah,
It's
it is
visible,
there.
right? Okay.
Yeah, it is visible.
The content, I mean, the PPT is visible for like, it's okay?
Students, are you okay? I hope you guys are watching through laptop or something, right? Through a system?
Or still I need to make it little bit elaborate, or shall I increase the font size?
You can make
Okay.
it a little bit big on the...
Because I have to give the explanation.
Okay,
So that's why I have opened a whiteboard also here.
Okay, that's fine. I think that's fine. Students, you need to confirm. Is everyone comfortable seeing the screen?
Yes, sir.
Yeah?
Okay.
Yes, ma'am. Yeah, you can start.
Yes. So hello students. A very good evening. So I think I have already started the S block elements a couple of weeks before. Correct me if I'm wrong. So today I'm going to take the S block elements. Today I'm going to complete the alkali earth metals, and tomorrow I'll complete alkaline earth metals. Okay. Is everything is clear? My audio and your visuals, everything is clear?
Yes, ma'am.
Okay,
Yes,
sure.
ma'am.
So you all I think you people were all present on my first class, right? All the persons who are present on my first class, or I'll give a small introduction, then I'll get back to the slide which I stopped on that day. Okay. Or if someone is missing on that day, someone absent, well, there is no response. Hello. Is everything is right on my side? Wait, I'll check.
Yeah, it is clear, ma'am. You can proceed.
Okay.
Yeah.
Fine. So I'll give a small introduction. As on that day itself, I have discussed more about the introduction. So the last electron, I mean the valence electron that enters into the s orbital, that is the s block elements. So s orbital consists of 2 electrons. So that's why there is 2 group. There is group 1 and group 2. So group 1 is alkali metals and group 2 is alkaline earth metals. These are all the basics and the introduction I have already discussed so far. Okay. So today we are going to see the introduction, trends, chemical properties, physical properties, preparations and uses. This is in your alkali metals. Okay. So moving to my first slide. So what is a diagonal relationship? So actually this thing will be elaborately discussed after scrolling the few more slides, but I'll give a small introduction. In periodic table, there are the elements like lithium. It is in group 1, lithium, sodium, potassium, rubidium, cesium. Oh God, wait. Okay. So next group 2 will be like beryllium, magnesium, calcium, strontium. So diagonal relationship connects this lithium and this magnesium. So they both will be having the similar characters in the sense the charge by mass ratio. Okay. So, have you heard about the diagonal relationship anywhere? I think you will be studied in your periodic table itself. There will be a slight introduction. You have already heard about this diagonal relationship in your periodic table. So, similarly, likewise, the third group of boron, aluminium. So, this beryllium and this aluminium both will be having the similarities. The similarities will be in terms of the atomic size and the ionic size and the oxides, the hydroxides, and if there is any connection between the dimers, or if they can form any kind of berylate ion or aluminium ion, and the halides and hydrides. Okay, so if you're just taking a very simple example, see, don't listen into the theoretical part, because my explanation will be completely different. If there is anything there highlighted, I'll be explained. Okay, so this is beyond, I'm just saying for your information. And if I'm taking the atomic size of lithium, it will be like 152 picometer. Okay, for magnesium it will be around 160 picometer. Exactly, for lithium, if it is 152 in the sense, it will be not for magnesium, it will be not for 152. So there will be quite the similarities. The differences will be there, but more or less they'll be equal. Okay, so that is how the diagonal relationship connects between the two elements. So this lithium and magnesium will be having a diagonal relationship. This beryllium and aluminium will be having the diagonal relationship. So this is what connects in the periodic table. And moreover, only we will discuss about these four elements. Okay, we will won't again discuss about the boron and silicon like that. Likewise, not only the diagonal relationship ends with the four elements. Clear? Clear, students?
Yes, ma'am.
Okay, next up. So here are introduction we don't need. Okay, so we are all know all the elements in the S block, the alkali earth metals, every elements will be having the valence electron of 1. So lithium, it will be having 1s2, 2s1. Okay, sodium, what happens? It will be having 1s2, 2s2, 2p6, 3s1. This is the valence electron, the outermost electron. So that is what I have mentioned here, ns1. ns1 in the sense that is the group valency. So all the elements in the alkali metals will be having the electronic configuration of ns1. Okay, so the valence electron present in the alkali metals will be 1. Okay, clear in this point? I think I have already discussed things, so I don't want to get into this much deeper. Atomic and ionic radii. So already I have discussed this atomic and ionic radii. So down the group, what happens? The atomic and ionic radii increases. Okay, the reason is because of the screening and shielding effect increases, and the effective nuclear charge also increases. But due to the screening and shielding effect is getting increased, that effective nuclear charge will become negligible. It will become constant. So I think I have already discussed about the screening and shielding effect and effective nuclear charge, right? What happens to the effective nuclear charge along the period and down the group? Yes, come on.
Oh, ma'am,
can't
along the period, it increases the effective nuclear charge,
Okay,
whereas
down
down
the
the
group,
group, it decreases.
it decreases, it will be negligible, and it will be remains constant. And along the period, the screening and shielding effect, what happens? It will be becomes negligible and constant. And down the group, the screening and shielding effect will be getting increases. So because of that only, this atomic and ionic radiate, what happens? Will be getting increased down the group as the number of shells is getting increased. Say for example, lithium, if this is the nucleus in the sense, the first shell contains 2 electrons and the second shell consists of 1 electrons, right? And for sodium, what happens? Again, another one more shell will be getting added. Okay, so the first shell consists of 2 electrons and the second shell consists of 8 electrons. So these are all basics you have already studied in your periodic table, right? So 6, 7, 8, and here there will be one more electron also present. So likewise, this shell no, it will be getting added up down the group. So what happens? Obviously, the atomic size will also getting increased. So that is what down the group, this atomic size will be getting increased. Okay. Similar thing applies for ionic radii also. And note with the third point, the monovalent ions are smaller than the parent atom. What do you mean by this in the sense? If lithium, after donating one electron, it will becomes Li plus. It will becomes a cation, right? So all the S block elements, alkali metals will be monovalent, okay? Because they will be having only the plus one as the valence electron. The alkali earth metals will be divalent, okay? So in lithium, what happens? This one will be having a size where Li plus in the sense it will donate the valence electron. Again, the size will be getting reduced. That is what the thing, the monovalent ions are smaller than the parent atom. Okay. So again, for this ionic radii also down the group, it will be getting increased. Okay. Clear? If there is any doubt, please ask me. Okay. Don't hesitate. Shall we move to our next thing? Am I going fast?
No, mom.
Someone? Sorry?
No, mom.
Mom, maybe
Okay.
slow down a little bit, mom.
Sorry, slow down a little bit. Yeah, I'll
Yes.
slow down. I'll slow down. Sorry. So far what I have explained, you have understand any doubts in any of the slides?
No, mom.
No. Okay. Next one is ionization enthalpy. You know, ionization enthalpy in simpler terms, if this is the nucleus, okay, and this is your shell, okay. So remove this valence electron. So the amount of energy observed, okay, note the point, in ionization energy, the energy will be observed to remove the valence shell electron. In electron gain enthalpy, the amount of energy will be released, okay, to gain the electron. So to remove this electron, the energy observed is the ionization enthalpy, okay. So down the group, what happens? Lithium, sodium, potassium, rubidium, and cesium. Okay, all these things are there. So for lithium, it is very, very small. Say for example, it is just having only 2 shells. So lithium will be not present as a lithium first of all. The lithium will be under the control of the nucleus, right? So the nucleus is the dawn here. So what it will make, it will control all the 2 shells. So what happens? You needed to give more energy. You need to absorb more energy to remove the valence electron. Whereas coming down the group, in sodium, again, there will be 3 shells. In potassium, there will be 4 shells. In rubidium, there will be 5 shells, and cesium, there will be 6 shells. So likewise, what happens here, the shells will getting increased. The screening and shielding effect plays a vital role. So what happens? The ionization enthalpy there, easily it can remove the electron for cesium. But for lithium, what happens? It is under the control of the nucleus and there is only 2 shells. Here you need to apply, I mean, you need to, the atom which is coming and removing the electron, it need to absorb more energy. So here the more energy will be applied and here there will be less energy. Okay. So down the group, what happens? The ionization enthalpy decreases. Okay. So decreases down the group. This is because of the effective nuclear charge. It will be increasing, but still the effective nuclear charge doesn't play any role. It is negligible. Because of the increasing screening and shielding effect, the ionization energy will be less for cesium and it will be more for lithium. Clear, guys?
Yes, mom.
Okay. So at any point, if you can't understand, please stop me. I'll explain one more time also. Okay. Yes. So next one is hydration enthalpy. Okay. I think you have heard about the Fazan's rule. Fazan's rule is nothing but, in simple terms, we can say all ionic compounds are not 100% ionic. It will be having a little bit covalent character in it. all covalent characters, all covalent compound will be not 100% covalent. There will be some amount of ionic character will be present in it. So that from that only he will say, as the ionic size is getting decreased, the polarization power will be increasing. Okay, so applied that thing, when the ionic size is very, very less, the hydration enthalpy will be very, very more. Okay, so that's why what happens, the decreasing trend will be following from the lithium to cesium. Okay, so common sense, we can use it, the common sense. Actually, for lithium, there is only 2 shells. So what happens, if the size is very, very less, the electron density also will be very, very less, right? So what happens, the attachment of the water molecule will be very, very more. That is, the interaction between the ion and the water molecule will be very, very more. Can you able to get my point, guys?
Yes,
Right?
ma'am.
Yeah. So in case of cesium, you just take a cesium. Okay. So what happens, it is ionic size. The ionic size of cesium will be very, very big. It is large. So the electron density will be very, very more. Sorry, it will be much more. So what happens there? The interaction between ion and the water molecule will be very, very less. So that's why the hydration enthalpy is following a decreasing trend from lithium to cesium. Okay, so lithium, which will undergoes the hydration, and it forms these kinds of hydrated salts. I'm not saying that cesium will not undergo hydration. It will undergo hydration, but the attachment, okay, but the bonding will be very, very big. But here, in case of lithium, it will be very, very strong. Okay, because the electron density is much more. But in case of cesium, the electron density is very, very less. The interaction between the ion and the water will be not that much efficient. Clear? So this is the trend follows, it is decreasing down the group. Clear, guys, of hydration enthalpy?
Yes, ma'am.
Okay, now physical properties. See, actually I have already discussed this thing, physical properties. So I have already said about the flame test also. So flame test, in the sense, when you're just heating your respective salts. So actually in the lab, we will perform these kinds of tests. We will dip it with dilute HCl or dilute H2SO4, any dilute acid. We will not go for the concentrated one, the diluted one, and we will show it in front of the flame. So what happens, it will be showing different colors. If it is a kind of lithium salt, it shows crimson red. If it is a sodium salt, it shows yellow. If it is a potassium salt, it shows violet. Likewise, what happens, it will shows different colors, which means when you're showing the salt in front of the flame, what happens there, the electron which is present in the ground state will be going to the excited state. Okay, once reaching the excited state, what happens, again, see, from going to ground state to excited state, the energy will be observed. Okay, the energy will be observed. Again, this electron needs to de-excite. So when it is coming from the excited state to ground state, the energy will be released. The energy will be released in the form of electromagnetic radiation. So there is different kind of electromagnetic radiation: UV, IR, visible, cosmic, X-ray, alpha, beta, gamma, all these kinds of things. So here in these kind of salts, what happens, if the electromagnetic radiations will be in the form of visible, so visible in the sense it will impact the color, whimsy or pattern. So that's why the following colors will be, we can get via the flame test. Okay, so this is the whole process happening in the flame test. And now what happens, the density. Okay, density you will discuss in the next slide. Okay, so another thing is melting point and boiling point. What is melting point and boiling point is based on the arrangement of the crystal lattice. What is lattice energy? What is the difference between the lattice energy and hydration energy? Can someone explain? Can you get my point? Students? Someone know, like, what is lattice energy? You don't want to say the hydration energy. What is lattice energy? You have already completed the solid state, right? Is my voice is audible?
Yes,
Hello?
ma'am.
So you are all listening me. So what is lattice energy? I think there are more than 10 members present here. Ashwath, Hamsini, Harshita, Kanishk, Shailaja, Shreyan Chetia, Shri Giridhar, Suprajit Sahu. So yes, 8 members present in the meeting and no one is saying what is lattice energy. You have already completed the solid state, right? Come on. Guys, well, you know or you don't know?
Ma'am, actually, solid state is there in 12th standard, ma'am.
Okay, it's there. What about states of matter?
Yes, ma'am.
In that definitely you will study about the crystal lattice. Lattice in the sense it's the arrangement of anions and cations. Okay, so you know, see, if the anions and cations, if it is like this, means you have to arrange it like this. Okay, so here the anion will be smaller, the cation will be smaller in size, the anion will be like this, it will be arranged tightly packed. That is the crystal lattice. This is a lattice energy. So the amount of energy released when the lattice is formed, that is the lattice energy. So hydration energy is nothing but when this lattice is dissolved in water, no. Okay, so when you're dissolving in water, there the energy will be released. So that is the hydration energy. Okay, so formation of this lattice is known as lattice energy. Okay, when you're forming the compound, the energy will be getting released. Okay, so this melting point and boiling point, how it is connected is, see, if it is very small, if you are just taking lithium, lithium is very, very small compound. Small element. So what happens? The crystal lattice of lithium will be very much tightly packed. Okay, so what happens when it is tightly packed? In the sense, it is hard to break the crystal lattice of lithium. Whereas coming down the group, if you are just taking the cesium, there will be very weak metallic bonding. Why it will be the weak metallic bonding? How you can say, see, metals in the sense, definitely this metal should donate the electron. Okay, so the main characteristic of metal is to donate electron. Okay, that is metals. So what happens? The bonding will be very, very weak. Okay, so lithium, sodium, potassium, rubidium, cesium, in the sense, cesium can easily donate its electron compared to lithium. So that's why what happens? The melting point will be very, very low because of the presence of the weak metallic bonding down the group. Clear with this thing?
Yes, ma'am.
Okay, see, you just don't see the theory. Okay, I'm differently explaining. This is something like different, which is like, this is your NCRT. I'm explaining in a different way. Okay, just imagine and you can understand. Clear? So down the group, the metallic bonding will be very, very weak. See, when there is a free electron in an atom, that is known as metal. Metals are all electron donors. They'll always donate the electron. That because of the presence of the free electron only, we are saying the metals are all the very good conductors of electricity. Okay, this free electron, no. See, if there is one free electron, this free electrons will be always revoluting around this shell. Okay, by this only it will conduct the electricity. Clear? So that's why we will say the metals are all good conductors of electricity. Clear? Okay, so we shall move to our next slide. Any doubt? Do you understand the flame test? Melting point and boiling point? Clear?
Yes, ma'am.
Yes, ma'am.
Okay. Now, what is this thing? Okay. Actually, it's just simple. See, when you're just see down the group, what happens? Your cesium, your rubidium, your potassium, they're all having more shells. Okay. So when there is any external source in the sense when it is like light or light is nothing but a form of electromagnetic radiation. So when you're just passing the light, see, if this is a cesium. Okay, just imagine this is a cesium. So when the light, what happens when it is like irradiated with the light or when it is like hit by any kind of electromagnetic radiation, this metal immediately loses the electron. Okay, because they're all metals. And if you're just taking the cesium or rubidium or potassium, what happens? There'll be a weak metallic bonding. So they will immediately lose this electron. Because of that only, they having many commercially and application orientedly they'll be using. So in many cells, the cesium and potassium is used as electrode in the photoelectrical cells. You will be studying the chemical energy. It will be converted into the kinetic energy. And finally, it will be converted into the electrical energy. Energy is interconvertible, right? That will be, you will be studying in your electrochemistry. So that is the thing. Because of the larger size, what happens when there is any external sources there, immediately it will releases the electron. Because of this property only, it is using in the photoelectric cells as an electrode. That is what they have been said in the point. Clear? Clear?
Yes, ma'am.
Okay. Now, okay. Just see this table. Okay. Yes. So atomic number don't go. Atomic mass, it's showing an increasing trend. Electronic configuration don't want. As I already mentioned, ionization enthalpy down the group, it shows an decreasing trend. There is no change. Hydration enthalpy down the group, what happens? Decreasing trend. Okay. See, don't take the negative in a max sign. Okay. Just to represent, they'll be using this negative. Okay. And metallic radius down the group, what happens? It will getting increased. Why the metallic radius down the group increasing? In the sense the property of metals will be very much more down the group, because cesium, the property of the metal is to donate electron. Okay, how quickly donating the electron matters. So cesium having larger number of shells. So what happens? It will easily donate the electron. That's why down the group, it will be highly metallic in nature, highly electropositive. Electropositive in the sense the tendency to lose the electron. So that is the thing. Metallic radius also what happens? It is getting increased, and ionic radius also getting increased. Melting point, as I already said, for lithium, we need to give more because of the arrangements of the crystal lattice. To break it, we need to give more amount of heating. Okay, so that's why it is showing this trend. And density, just see the exception case. 0.53. Actually, density, what happens? It's showing an increasing trend. In case of sodium and potassium, you can see this sodium is more denser than this potassium. How?
Ma'am, because volume of the sodium is less than that of potassium.
Volume of sodium is less than potassium. Oh, correct. Okay. So density is nothing but, oh my God. Okay. So density is nothing but it is mass by volume. Clear? So mass by volume in the sense mass should be inversely proportional to volume. Clear? So if it is inversely proportional to volume in the sense, what happens in that case? The mass, if the mass is increasing, the volume should parallelly decreasing. Okay. So what happens there? The volume is also getting increased. The reason is, see, the nucleus is there and the shell is there. Wait, I'll draw it. The nucleus is there. For potassium, there will be 4 shells. Okay, this is the thing. This is potassium, imagine. Okay, so this nucleus will be in a very happiest mode. Why? In the sense there will be more electrons surrounding around it. So what happens? It will try to attract all the electrons, right? So first initially it will try to concentrate on this shell, and it will concentrate on this shell, and again it will concentrate on this shell. Okay, so what happens? So when it is concentrating on each other's shell, it can't pull the outermost shell that much efficiently, because the first shell it can pull very maximum efficiency. Here the efficiency will be little bit less, here much more less, but here it can't concentrate. So what happens? The volume will be, so when it is not at all pulling inside, what happens? The volume will be getting increased. So if the volume is getting increased in the sense, what happens? There is a disproportion will be carrying over there, and so that's why what happened? The potassium will be having the sodium will be having more and the potassium will be having less. So that's why the clear thing is the sodium will be more denser than the potassium. Clear? Clear, guys?
Yes, ma'am.
Okay. So only this exception, please follow. Okay. And the rest of the things, there is no exceptions. And now look into this thing, standard potential. What is standard? This is nothing but standard reduction potential. Have you heard of standard reduction potential? Anywhere? I think in electrochemistry you will be reading this thing. Standard reduction potential. Standard reduction potential in the sense it should be a very good reducing agent. Okay, what is reducing agent? Guys, what is reducing agent? What is oxidizing agent? What is oxidation? Have you completed redox reaction?
I mean, ma'am, addition of oxygen or loss of hydrogen or proton.
Okay, so oxidation in the sense loss of electron. Okay, so reduction in the sense gain of electron. So there will be the ulta. Okay, vice versa, topsy-turvy thing. So reducing agent in the sense it will gain the electron, it will make the other substance to reduce. Okay, so that's it. So you can see you just don't need to see there is the values. You don't need to compare the values. You can see all the elements shows the higher negative standard reduction potentials, which means every element is a reducing agent. Okay, because they're all highly electropositive and they're all ready to lose the electrons. So reducing agent in the sense what happens, they that's why here they have been said they're all having the higher negative values. Okay, being highly electropositive and they can easily donate the electron. So that's why the standard reduction potentials of this alkali metals shows the higher negative values for all the 5 values of this elements. Okay, so this thing are all experimental value. Okay, so here everything has been done by your electrochemical process. Okay, so you don't need to worry about the values, and I think this is not going to be coming in your exam point of view. Just know the alkali metals will be having the highest negative standard reduction potentials because they are all the strongest reducing agents in nature. Clear?
Yes, ma'am.
Okay. See, if anyone is having the doubt, please raise your voice. I think so far, somewhere you should be arriving with the doubt. I don't know why, whether you have understood or not. Okay. Mystical. Next is reactivity towards air. Okay. So generally what happens in alkali metals, so if you're taking the, the alkali metals means some alkali metals can be obtained in earth crust. Okay, when it in compound forms, it can be like if you are just taking the sodium chloride, which is present in the compound form, it can be obtained from the ocean. So as a different kinds of things, it will be available. Okay, so this alkali metals, what happens in the sense when it is reacted with oxygen in air, atmospheric air, immediately it forms their respective oxides. Okay, so everything will form the oxides, but the dissimilarity is not all the elements in the alkali metals will form monoxide. Not all the alkali elements will form peroxide. Not all the alkali elements will form superoxide. So the lithium here, it forms 4Li. Sorry, here Li2 will be there in the subscript. Okay, it will be like this 2 Li2. Okay, so it will be like this. So this is lithium monoxide, sodium peroxide, and this metal corresponds to potassium, rubidium, cesium. They form superoxide. Okay, so first of all, you know the concept, the smaller cation can stabilize the smaller anion. Okay, the bigger cation can stabilize the bigger anion, and the smaller cation cannot stabilize the bigger anion. Okay, this is the basic concept. So being very much small in size, the lithium will only tends to form the monoxide. Okay, and sodium, which is comparatively little bit larger than the lithium, it forms the peroxide. And rest of the three elements, potassium, rubidium, and cesium, the size will be little bit larger than the lithium and sodium. They form their superoxides, where the larger cation can stabilize the larger anion. So what happens here? Oxygen, O2 molecule, which will be large in size. Okay, so you will be studying in your redox reactions. So what happens comparatively? All the three bigger cations can stabilize the bigger anions. It forms superoxides. Okay, so the difference is the lithium will tends to form monoxide, the sodium will tends to form peroxide, and this metals, which is potassium, rubidium, and cesium, will tends to form superoxides. This you have to know and you have to remember. Even in exam point of view, even in the competitive level point of view, you have to know this thing. Because of its size, there is a variations in terms of oxides also. Clear with this point, guys?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. Reactivity towards water. So with water, what happens? Every alkali element will form their respective hydroxides. Okay. So they're all water soluble. So what happens? Everything will form their respective hydroxides. So if this is nothing but, I'll write another reaction. If you take the metal as sodium, okay, when it is dissolved in water, what happens? Your sodium hydroxide, that is nothing but your caustic soda with the release of hydrogen gas will be formed. So likewise, lithium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide will be formed. So here I have just dissociated ions are represented. For your understanding purpose, you can write like this. Clear? So every alkali element will form their respective hydroxides. There is no change in it. Only in oxides, it will be forming monoxide, peroxide, and superoxide due to the size. And also the concept, smaller cation stabilizes the smaller anion. So clear with this slide?
Yes, ma'am.
Okay. See, another one more thing is, in inorganic, the S block and P block, you have to go through the preparations daily by daily. Okay, in daily, actually, day-to-day practice, keep on studying the preparations. There is no, trick or there is no hint to study the preparations. Only one hint is there. Only in hydrolysis, what happens, the oxidation state, what you have taken for the reactant will be same in the presence of product is the only trick. Rest of the things you have to go through the reactions on the daily basis and the daily practice, because in physical chemistry you will be only learning and you have to be like, you will be thinking, but this inorganic is theoretically you have to go through it, and you have to go through the reactions, because in P block there is 6 families, and 6 families you will be covering around of up to NCRT like 200 to 250 reactions. So you have to daily study, then only it will be working out for your exam or as well as the competitive point of view. Okay, now I'm getting to, for 11th P block, there is all 6 families, or how many families will be covered in your chapter?
Mom, I think only three to four, not all.
Boron, carbon, and oxygen. Okay, fine. Next, reactivity towards dihydrogen. So here what happens? This dihydrogen, in the sense, all the alkali metals, when it is reacted with hydrogen, H2 is hydrogen, but in chemical point of view, in chemistry point of view, they have mentioned as dihydrogen. They form their respective hydrates. Okay, and what happens here? You can see all the elements apart from lithium. Okay, God, sorry. So this lithium is having the greater temperature, okay, to form the hydrates because of its size. Okay, it is very smaller in size. The hydrogen is also smaller in size, right? Correct. The size of the hydrogen is very, very small. It is just having only one shell. So being this lithium also small and the hydrogen also small, you need to create a process, chemical process. You need to arrive the product, means here you need to increase the temperature. That's why for lithium, the temperature is 1073 Kelvin. Clear? And for rest of the elements, apart from lithium, sodium, potassium, rubidium, cesium, everything will be the temperature of 673 Kelvin. Because of its size only, for lithium, the temperature is, we will be keeping the temperature at the higher range. For rest of the thing, it will be only 673. And also, why the alkali metal hydrides will be having the high melting point? Why it is having high melting point?
Because is it because they have a small atomic radius?
Exactly. See, smaller, okay, wait, I'll come to your point. You're saying smaller size of alkali metals means cesium having larger size, right? Rubidium, cesium, they're all having larger size, no? So why you need to give more melting point? There is no range. Okay, see, the only thing is hydrogen is a small molecule, right? So what happens, hydrogen, when it's going to act, when it is involving in a reaction, it will go and tightly attach to the cation. Okay, so what happens, being a small molecule, it will go and tightly combine with the cation. So that's why we will be giving the more melting points for this metallic hydrates, because of the size of the hydrogen. Okay, being very, very small, the attaching power will be very, very more towards the cation. That's why they will be giving high melting points. Clear? Clear, guys?
Yes,
ma'am.
ma'am.
Okay. Yes. Reactivity towards halogen. So here, little bit thing is just we need to know. Actually, we have already studied about the Fazan's rule. So if you know about the Fazan's rule, this is what the thing will be. Right. Okay, we can take the sodium itself and as an example. Okay, yes. See, sodium, okay, what happens? It will donate one electron. Being a metal, what happens? It will become Na plus and the size will be very, very less. And chlorine, it will be like accepting the electron, it will become Cl minus, it will be bigger in size. So what happens? This chlorine, after donating the electron, the size will become very, very small. Once the size is getting very, very small, what happens after this is the nucleus will be more powerful. So what happens? See, it will be, there will be all the electrons will be here. Okay. So what happens in the sense, it will start to take the electron, which means This is an ionic thing, right? Actually, I already in Fazan's rule, we have learned about this thing. That is, all ionic compounds is not 100% covalent in the sense NaCl is an ionic compound. Have you, I think you have known this thing, right? You have studied, you have completed your chemical bonding.
Yes,
Yes or
ma'am.
no? Okay. So from that you can know, see this NaCl is an ionic compound, right? But we can't say this is an 100% ionic compound. So what happens? This Na, sodium, being under the influence of nucleus, due to the high effective nuclear charge, what happens? It will try to take the electron, and finally a distortion will be happening like this. So what happens? The one electron will come and sit here. All the electrons will be there. The one electron, what happens? There will be little bit of sharing will be happens here. Okay, this is the distortion. This is the distortion happened by the thing. Similarly, what happens here? Can you understand this point?
Yes, ma'am.
Okay, so the similar thing apply in this process. So here what happens, just leave lithium. Lithium is being very, very small. Okay, it can't share the electron. So what happens, sorry, it can't completely transfer the electron. Okay, so it will can only share the electrons. See, lithium is just having one shell and two shell. So what happens if it share the electron in the sense, it will lose its one shell. So what happens? It will only try to share. It will not completely transfer. So lithium will not act as an ionic halide. It will completely act as a covalent halide. But rest of all the elements, sodium, potassium, rubidium, cesium, all the elements will be acting as a covalent halide. Okay. So for this only, the what I have explained is actually theoretically mentioned here. So I don't want to again explain. The electron cloud is nothing but the electron cloud will be revolving around here. Once after the electron has been taken, I mean shared by the electron, shared by the sodium, the distortion will be taking place like this. Okay. So lithium being very, very small, what happens? It can't share. Sorry, it can't transfer. It can only share. Rest of the thing, what happened? It can act as an ionic field. Clear with this point?
Yes, ma'am.
Okay, now let me say another one more thing. If I'm taking, so from in this sodium, in sodium is small and chlorine is large. If the size, if the cation is small, if the anion is large, the distortion will be happens. Okay, so if I'm taking lithium fluoride, lithium chloride, lithium bromide, lithium iodide, which one will be having more covalent character?
Lithium iodide.
Because exactly you're right, because you can see this is a larger anion, right? If it is a larger anion, the distortion will be takes place, and this lithium can easily share its electron. Clear? So that is why this will be showing the more covalency. Okay, the covalent character in lithium iodide will be very, very more. Clear with this point? Clear with this slide? Any doubt?
No, ma'am.
Okay, next. So tomorrow for your online class or live physical class?
Ma'am, I think it's
Sorry?
online only.
Online only. Okay. Next one is reducing nature. Yeah, coming to the point. As I already said, this alkali metals are a very, very, very much strong reducing agent. Okay. Out of the everything, lithium and sodium both acts as a strong reducing agents. Okay. See, the lithium will be the more, I mean, like most strong reducing agent, and then the sodium is the least. Okay. So the reason because of this standard electrode potential. Do you remember the standard electrode potential? I have already discussed in the previous slides. You can see You just see the high negative standard electrode potential value. I have already mentioned here. You can see the high, see, they're all the high standard reduction potential values. Because of this only, they're having, oh God. Okay, because of this only, this lithium and sodium, of course, all the alkali metals are reducing agents. But the thing is, which is more powerful in the sense, first one is lithium, second one is sodium, because of its highest standard reduction values. And another one more reason is the hydration enthalpy. Because of its small size also, another one more thing comes in the point. So what happens, it can easily convert the solid into gases. That's the one point. Easily donates the electron. Okay, and the hydration enthalpy for lithium, what happens here in the sense, easily it can easily undergo hydration because of the electron density will be more. So because of these two things, the reducing nature of alkali metals will be very, very more, and they're all strong reducing agents. Out of all the elements, lithium will be the most strong reducing agent, and the second most powerful is the sodium. Clear with this point?
Yes, ma'am.
I got disconnected, ma'am. Could you repeat what you just said?
Okay. Yes. See, in all the alkali metals, all are the strongest reducing agent, and also every element has a highest reducing power. Out of the 5 elements, the lithium will be lithium will be most strongest reducing agent, and the second most will be sodium because of its hydration energy. Okay, because of its small size. Clear with this thing? That's why I have noted it can easily converts the solid into gases. It can easily donates the electron, and the hydration enthalpy also very good in terms of alkali metals. Okay, see the comparisons, if you're just comparing all the ionization enthalpy, all the hydration enthalpy, means of course there will be the variations will be there, but everyone will undergo hydration enthalpy. Okay, only the thing is lithium undergoes more hydration enthalpy. The attachment of the interaction between the ion and the water molecule will be more, and the interaction between the cesium and the interaction between this in cesium, the interaction between the ion and the water molecule will be less, but it undergoes hydration enthalpy. Because of this reason only, they are all the strong reducing agents, and lithium is first, sodium is second. Clear?
Okay, ma'am. Got it.
Yes. Next. Yes. Interesting. Solutions in liquid ammonia. Wait. Okay. See, don't read this thing out. See, this metal is of any alkali metals. Okay. You can take lithium, sodium, potassium, rubidium, cesium. Now, X plus Y moles of ammonia. So you're taking the metal. Okay. This ammonia is of liquid ammonia. Okay. So you're just what happens, you're in actually this experiment, you can see it in YouTube, or if there is any social media platform, exactly there is one site for it. They'll do it and they'll exactly show it for your very good remembrance. Okay, so what happens here in liquid ammonia, X plus Y, you have we have denoted this X plus Y moles in the sense, see, metals, when it is introduced with this liquid ammonia, what happens, it will tend to release its electron, right? So that's why we have taken X plus Y moles. Clear? So the metal will take one kind of ammonia, the attachment, okay, X moles of ammonia, and the electron which is released, no, clear, that will take another moles of ammonia, that is Y moles of ammonia. That's why we have taken X plus Y moles. Clear, guys? Can you able to get my point? Yes or no? Hello?
Ma'am, I don't understand.
Okay, wait. See, this is a metal. Okay, these are all the alkali metals. This can be of any metals of sodium, potassium, lithium, rubidium, cesium. So here we have taken the ammonia. My explanation is why we have taken X plus Y moles. Okay, why it is denoted here as X plus Y moles in the sense, what happens when you're introducing into the any liquid solution or even if it is in water, what happens? It will immediately tend to release the electrons, right? This is what the common thing the metal would exhibit, right? So what happens if you're taking any other reactant? Okay, so the properties of the metal will be like, so if I'm taking any reactant, what happens if I'm taking here ammonia in the sense, this ammonia will go and attach with metal cation, it will also will go and attach with the released electron. Clear?
Okay, ma'am.
If there is a beaker, okay, so if there is H2O molecule, okay, so in water molecule, it will be dissociate H plus and OH minus. This is a major thing. Hydrogen is being a high dielectric constant. What happens? It will try to break if there is an alkali metals is present in the solution. So what happens? It will tend to attach. So that's why X plus Y moles of NH3 is represented here. Now what happens? The metal, it will, after releasing its electron, it will becomes the cation. That's why the plus is represented here. MNH3 X, that is X moles of ammonia, and the electron released, that will be of 5 moles. Now, carefully listen what happens. This electron has become the ammoniated electron. Okay. Why? In the sense, it has attached with this NH3. So what happens? It will absorb the energy. Once it is absorbing the energy, what happens? After some time, definitely it needs to release the energy, right? After releasing the energy will be released in the form of electromagnetic radiation. Here it is in the form of visible range. So that's why it impacts the blue color to the solution. Okay, if you drop alkali metals, okay, what happens in a liquid ammonia? Suddenly, after some time, what happens? It will impact blue color. In beaker, it will resemble as a blue color solution. Why? What happens? The released electron by the metal will go and attach with the ammonia. What happens? It will become the ammoniated electron. Okay, so what happens? The electron will absorb the energy, right? Once after absorbing the energy, what happens? Definitely it needs to de-excite. So it will release the energy. And what happens? The electromagnetic radiation will be released, which is here in the form of visible region of light. So that's why it is blue color, which is imparting to the solution. Clear? Just only this reaction. Clear? Only this reaction you guys got clear with this?
Yes, ma'am.
Yes,
You
ma'am.
have to imagine this thing. Okay, yes. Now, this is one thing. After what happens, see, if there is in water, if you're dropping the metal, there is not only one reaction takes place, thousands of reactions will take place. Okay. After that, what happens? The metal is there. Okay. So there will be some free electrons will be also revolving around it. Right. So what happens? The free electrons, there will be some electrons will go and attach with this ammonia, and it forms the ammoniated electron. There will be some electrons will be revolving as a free electrons. So that electron again, which will be go and attach with this metal, and finally it forms amide. And this amide will be of, what happens? It will be of brown color. So what happens when it is attaching with this metal? Again, it will absorb the energy and it will release. That will be in the form of electromagnetic radiation. And in the visible region, the bronze color will be obtained. And here there is an unpaired electron. So it is paramagnetic in nature. Here there is no unpaired electron, which is diamagnetic in nature. Okay. So the main concept is to understand the color of the solution changes. Okay. When initially you're dropping the metal into your ammonia, initially the blue color will be obtained and finally the bronze color will be obtained. And what happens? That will be resulting in the formation of the amide. Clear, guys? Any doubt? Do you guys understood or not?
Yes, ma'am.
Okay. If there is any doubt, please ask me. This is a very important reaction according to your syllabus. your board exams. Okay, so just remember, when it is reacting with ammonia, what happens? It easily releases the electron. Everything has happened in a single beaker. Okay, in a single beaker with a liquid ammonia and the metal, this is happening. Okay, so there will be an free electron, and again what happens? This unpaired electron will be just go and paired up in the metal, and again it will impact the bronze color solution. With that bronze color solution only, we came to know the amide is formed. Okay, so initially the two-step process is happening, and in YouTube also you can go and see this reaction. If you're interested, you can see, they'll show about the changing of colors also. Clear? Now we can move on to next slide. Any doubt in this slide? This is very important. Okay. Okay. So next one is uses of alkali metals. Do any of the persons having any doubt in the previous slide? Yes or no? No? Clear with the previous slide?
Yes, ma'am.
Yes,
Okay,
ma'am.
next. Uses of alkali metals. I think uses you can go by yourself itself. Okay, so I'll simply say the important things. Okay, see, this lithium metals is actually lithium in many commercial purpose. It was not used as only lithium. It is used as alloys. Alloys in the sense, mixture of compounds. Okay, all the compounds is mixed, and in that one of the component lithium is used, and it is used as a in motor engines, white metal. That's you don't know. Okay, aluminium is used in aircraft parts. So in the wings that is present in the aeroplane, it is made up of aluminium because it's highly durable. Okay, so that's why aluminium is used there. And magnesium in using armor plates, in the sense, in olden days, the soldier who is going for the fight, they used to put one kind of iron clothing. So that is nothing but the magnesium metal. In thermonuclear reactions, it is used. And this sodium is used in sodium lead alloy. This is nothing but tetraethyl plumbane, tetramethyl plumbane. Okay, actually these are all the alloys, mixture of compounds. You don't need to worry in this. You just need to inform. These organolead compounds were earlier used in anti-knock additives, in the sense, actually, in the two-wheelers that we are used, there what happens, there is something called fuel octane. Have you came across this word, fuel octane? Fuel octane, which is the capacity, the amount of fuel that can be filled in the tank. Okay, it shows a kind of the digits, mathematical digits. So what happens, that fuel octane can be obtained by increasing the temperature and pressure, which makes the auto ignition of that vehicle. So for that only, this anti-knock additives to petrol, because the efficiency of petrol will be getting less. So that's why it is used in there. And liquid sodium is used as in a faster breed reactions. And potassium, which is present in our body, and for agriculture it is used as a fertilizer. And soft soap. What is soft soap? It is nothing but your gel bathing bar. Okay, liquid soap, moisturizing gel, or anything, that is nothing but the potassium, because maximum in liquid soap they'll use potassium rather than using sodium. Okay, and excellent absorber of carbon dioxide. And as I already discussed, cesium, they can easily and readily lose the electrons. So that's why it is used in the photoelectric cells, where the energy can be easily interconvertible. Clear? So this thing and all, I think you can go by your own uses. So shall we move to our next slide? Any doubt in this?
No, ma'am.
Okay, just go through the uses, okay, in your textbook itself. Next, oxides and hydroxides. Okay, okay. So this is the important point. See, this is nothing but the oxide. Okay, this is lithium, which forms your monoxide. This is lithium monoxide. This is sodium peroxide. And this metal is nothing but your potassium, rubidium, cesium superoxides. So what happens if you're taking these oxides, when you're dissolving it in water, what happens in the sense, every oxide, peroxide, superoxide, after dissolving water, it forms their respective hydroxides. So you don't confuse this M plus OH. This is nothing but an MOH, that is lithium hydroxide, sodium hydroxide, like that. Okay, everything will form their respective hydroxides, but lithium is very, very small. So what happens, only there will be the formation of hydroxide. In case of sodium, you can see the hydrogen peroxide is released. In case of potassium, rubidium, cesium, it is a superoxide being a larger anion. Okay, so what happens here? It releases H2O2 as well as the oxygen gas is released. Okay, this is only because of the size. So lithium being very much smaller, there will be only the formation of hydroxide. But in case of sodium, it is a peroxide, so there is a release of H2O2, hydrogen peroxide. In case of superoxides, you can see the oxygen gas is also released along with the hydrogen peroxide, and there is the formation of hydroxides also. Okay, so this is also very, very important in your exam point of view. Clear with this point?
Yes, ma'am.
Okay. Okay, oxides and hydroxides. Okay, so actually, if you just go through these 2 points, it's very, very simple. This the thing is, you can see this oxide, hydroxide, superoxide, everything you can be prepared. The thing is, as I already said, the stabilization of larger anion by larger cation. Okay, so this is actually done to the lattice energy. In lattice energy, what happens? We will say that, okay, this cation will be small, the anion will be large. But the thing is actually more or less, it will be like only this much. Okay, it will take some time to load. I don't want to get into that thing. If cation is of this kind, anion will be little bit anion will be larger. Okay, there will be not a major difference. Okay, so the larger cation is stabilized by the larger anion. So this has been done by the lattice energy. Why lattice energy? In the sense, there only the arrangement of anion and cation will be perfect to make it as a crystal lattice. Okay, that's why the stabilization is speaking here. So these oxides, what happens? Easily they form the hydroxides. That is what the reactions they have been denoted here. It's just an explanation they have been given. You have to know this point. Larger anions can be stabilized by the cations. That's it. So down the group, what happens is stability, solubility, everything will be getting increased. That's it. And this oxides and peroxides are colorless. Okay, this superoxides being large in size, what happens? They can easily exhibit from the ground state to excited state, and they can impact color. That's why yellow or orange color. Okay, so this oxides and peroxides, mostly they'll be colorless, but the superoxides will be yellow or orange in color. And the sodium peroxide will be acts as a very good oxidizing agent. Oxidizing agent in the sense where it involves loss of electron. Okay, so loss of electron means sodium peroxide ready to lose the electrons. Okay, so it is one of the uses only. Next, halides. Coming to this point, all the alkali metals will form their respective halides. Okay, so here you can see they can be prepared by the reaction of the appropriate oxide, hydroxide, or carbonate with the aqueous hydrohalic acid. So this thing I have to write and explain. Okay, so now take this thing. First thing, I'm explaining it with oxide. We can take lithium oxide. Okay, so this is next one. We are treating it with hydrohalic in the sense HX. This X can be of chlorine, fluorine, chlorine, bromine, iodine. You can substitute any acid in it in this form. So that's why it is X. Okay, so this X can be of any halogens. So when it is treated with this form, what happens? You will be obtain your alkali metal halide, which means, so 2 will be there to balance it. So it will be like 2 LiX plus this water molecule will be getting out H2O. Clear? Okay, so that is what they have said here. First one is oxide. Now I'm taking hydroxide of anything. So I'll explain with sodium hydroxide, NaOH. Again, I'm treating it with HX, that is hydrohalic acid. This X can be of any kind. Okay, So what happens directly, this H2O will be getting out, water molecule, and your alkali metal halide, that is NaX, will be obtained. Clear? And third one is carbonate. So I'll write K2CO3, which is treated with hydrohalic acid. So what happens? Water molecule should be getting removed. So 2 should be added here. So it will be like 2KX, that is your alkali metal halide, plus 2H2O will be getting removed. H2O, and another one more O means CO2. Okay. So this is what they have been said. If you're taking the oxides, when it is reacted with, see, you can use anything. I'm just using it as an example. When I'm treating it with hydrohalic acid, your alkali metal halide is obtained. With hydroxide, when I'm treating with hydrohalic acid, again your alkali metal halide will obtained. With carbonate, again your alkali metal halide will be obtained. So likewise, you can the formation of alkali metal halide will be formed either with oxides or hydroxides or carbonate, with any kind. And this alkali metal hydrates are all highly melting. Okay, they have high melting point, colorless, and they are crystalline solids. And because of this hydrohalic acid, they'll be having high negative enthalpy of formation. Okay, so this is the range. So do you understand this concept? What I'm trying to say? I'm trying to say about this alkali metal halide. This can be of LiCl or LiBr, anything, or NaCl, anything. Okay, so that's why I have represented it as X. Clear with this equation? Clear with this reaction? Clear with this 4 lines?
Yes, ma'am.
Okay, now coming to the next 3 lines explanation. See, if I'm taking lithium fluoride, okay, I'm taking all the things: sodium fluoride, potassium fluoride, rubidium fluoride, and cesium fluoride. This delta FH0 is nothing but your enthalpy of formation. Okay, so what happens is enthalpy of formation, it will be more negative, most negative on the top, while coming to the down, on down the group, what happens? It will become least negative. What's the reason? See, that's what they have been said. Fluorides become less negative as we go down the group, while the reverse for chlorides, bromides, iodides. So del FH0 always becomes less negative from fluoride to iodide. Okay, so what happens? See, you can just, I have taken here fluoride. Okay, you can also compare it with like lithium fluoride, lithium chloride, lithium bromide, or lithium iodide. If you're just taking in this process, again in this process also, this will be more negative, most negative. And this will be least negative. Why? This is in terms of enthalpy of formation. First, what is enthalpy of formation? Guys, can you understand what I'm trying to say? Are you able to understand these 2 columns? I'm asking the question why it is more negative, why it is least negative in terms of this delta FH0 is nothing but your enthalpy of formation. I'm asking why it will be more negative. This trend will be followed for this alkali metal halide. Whatever combination you're taking, the fluoride will be of more negative. It's very simple. Do you have any idea? Yes or no? Say yes or no, guys.
Mom, is it because cesium is more electropositive?
Okay, down the group, electropositive increases. See, fluorine is the most electronegative element in the periodic table. Fluorine is the most electronegative. The second most electronegative is oxygen. The third most electronegative is nitrogen. This is highly electronegative. This is the smallest in size. So that's why this impacts most negative value in the enthalpy of formation. Clear? Always the fluorine will be impacting the more electronegative. You know, I think you know this, right? In the periodic table, if you are taking all the 118 elements in the periodic table, fluorine is highly electronegative. Second most highly electronegative is oxygen. Third most highly electronegative is nitrogen. Clear? Yeah.
Yes,
Can you
ma'am.
able to? Yeah, that's why. That's the reason. Okay. This enthalpy of formation is nothing but where this compound is formed. Okay. So this one will be very actually this product, this this lithium fluoride will be very much stable. You can't easily break it. This will be most negative because this is very much smaller and this is highly electronegative. Highly electronegative in the sense it will tend to attract the electron. So what happens? The bond that is shared by this two element will be very strong. Okay, so that's why it's most negative. This is least negative, and here also this will be most negative, this will be least negative. Can take of any other combinations. I'm writing it as LIX, NaX, KX. Just write it as X because you can make it as any permutation combination. Okay, so this will be always most electronegative, sorry, most negative, and this will be least. Okay, that is what they are trying to say here. Sorry with the pen management, I don't know. Okay, so got my point with this three line. Clear?
Yes, ma'am.
Okay, now connecting the above thing. See, so what happens? This is most strongest one, is not easily to break. So more melting point and boiling point, obviously you will give to fluoride, right? So that's why fluoride is having the more melting point and boiling point, and chloride and bromide and iodide. Clear with this one?
Yes, ma'am.
Okay. Now coming to the next part. See, out of this there is some exceptional cases. Which one is? See, lithium fluoride and cesium iodide. They don't easily dissolve in water. The reason is lithium fluoride, as I already said, this is being very small. So what happens in the sense, the lattice energy, no, what happens, it is very small. The arrangements of all the anion cation will be very much closer. It is not that much easy to break. So when you are just putting this lithium fluoride into the water, it will not easily dissociate. So that's why due to the highest lattice energy, what happens, it will show a very less solubility. In case of cesium iodide, what happens, the hydration enthalpy is very less. Okay, which means the interaction between the ion and the water molecule is very less. So due to that thing, it shows the low solubility. So these two compounds will be soluble in the organic compounds. Okay, clear with this point? Why lithium fluoride is showing the low solubility? You may have the doubt. Lithium is having the higher hydration enthalpy, but fluorine is like highly electronegative, right? It will won't leave the lithium. So what happens, because of this fluorine, it will be having the highest lattice enthalpy. So that's why low solubility. In case of cesium, because of the hydration enthalpy, what happens? It will shows a less interaction between the ion and the water molecule. That's why this shows the exceptional cases in the solubility in water. Okay, so that's why they'll be always dissolved in the organic solvents. Clear? Clear, guys?
Yes, ma'am.
Okay. So this inorganic chemistry only, it will actually go only in this process. Okay. It's full of theory. But organic and physical will be quite interesting. Okay. Next one is salts of oxacids. So first of all, what is oxoacid? Can you say any example of oxoacid?
Sulfuric acid.
Very good. Sulfuric acid, phosphoric acid, carbonic acid. Okay. So how we are saying that as an oxoacid?
Because it contains
you say?
oxygen.
Wait. Let me draw. See, I'm taking phosphoric acid. This is a structure. P double bond O, H3PO4, right? So H3PO4 in the sense, it'll be of this kind. Okay. So what happens? This double bond, oh no, this is known as oxo group. Okay. All these OH, no, they are ready to give the H plus, which means they are ready to change into an acid. Okay. So that's why this is known as oxoacid. So which follows in terms of sulfuric acid. If you take sulfuric acid, it will be of this kind, H2SO4, which means like these structures you will already drawn in your loose dot in chemical bonding. So 1, 2, H, O, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. H2SO4. This is the oxo group, okay? And this will be removed as H plus acid. So that's why it is oxoacid. And carbonic acid will be like C double bond O H2CO3, which means like, okay. Okay, so this is the oxacids. So what they are trying to say here in the sense, all the alkali metals will react with this oxo acid, with all these oxo acid, and they form their respective salts. Okay, which means I'll say the example. Okay, if I'm taking any metal, any alkali metal, I'm taking sodium. Okay, sodium. Okay, if I'm taking with sulfuric acid, so what happens? It will be getting a as to balance Na2SO2, sodium sulfate, and your hydrogen gas will be getting released. Okay, so if I'm taking with carbonate, sorry, with carbonic acid, Na2CO3, and here also your hydrogen gas will be getting released. Okay, so what happens? So literally the overall information is any alkali metal that can react with the salts of the oxo acids and they can form their respective salt, sodium sulfate, sodium carbonate, sodium phosphate or rubidium sulfate, anything they can form. So finally at the end, what happens? They form their respective salts. So in this, the exceptional case, if definitely there will be an exceptional case, which means this sodium sulfate, okay, sodium carbonate, sodium hydrogen carbonate, they're all like thermally stable. But if you're just taking the lithium, okay, when lithium comes under picture, what happens? The size of the lithium is very, very small. But the lithium cation is very, very small. If you take the carbonate anion, it's very, very large. Okay, as we already discussed, the smaller cation can't stabilize the bigger anion. So what happens in that case? If Li2CO3 compound exists, means it will be unstable. See, slow, little range of heat is enough to diffuse it. Okay, so what happens? Easily it will dissociate into lithium oxide and carbon dioxide. So this is thermally unstable. So if you're just taking lithium hydrogen carbonate, this is not at all existing compound. Okay, so apart from lithium, down the group, everything it shows it will react with the oxo acids and it will form their respective salts. So lithium, what happens? It will form, but the thing is, it will be unstable. Okay, it will be unstable in the environment, and thermally also it will be giving. It will be unstable. So clear with this point?
Yes, ma'am.
Okay. Now, coming to the thing is, if I'm taking lithium carbonate, okay, sodium carbonate, potassium carbonate, rubidium carbonate, down the group, what happens? The stability and the solubility, both the things will be getting increased. Okay, because lithium, it's not stable. So what happens down the group? The stability and the solubility of this carbonates will be getting increased. Okay, so that's what I think they have been mentioned here. Okay, generally soluble in water and they are thermally stable. So what happens as the electropositive character increases, the stability of carbonates and hydrogen carbonates increases. And the lithium carbonate is not stable to heat. So it will be easily decomposed into lithium monoxide and carbon dioxide. That's what they said here. Clear? Clear with this point?
Yes, ma'am.
Okay. So there is no doubt. I think so far we have moved up to 15 slides. So no doubt you're as much as clear, that much clear. You guys really, I can't believe. Seriously, everyone got everything. There is no doubt. I think by now you have really, you should at least ask me 5 to 10 doubts because I'm expecting. But see, there is two things, two permutation combination. One is if you understood everything, the doubt will be not there. If you don't understand anything, that time also there will be no doubt. I don't know in which category I can add you, first or second. Seriously, no one has no, like, there is no doubt so far. Oh my God, you're all maintaining the silence, which means in what note I can take this? Come on, open your mouth.
No doubts, ma'am.
Seriously? Okay. So wait, let me go to the. Okay. Shailaja, there is no doubt for you.
No, ma'am.
So shall I ask the question? Shall I ask the question? Right now, there is no answer is coming from your side. Come on. What about Kanishk? No doubt. Suprajit, Harshita, no doubt. Seriously. Okay.
No, ma'am.
That's okay, fine. See, I'll one more thing is I'll give my WhatsApp number. If there is any doubt, don't hesitate, don't be reluctant. Okay, just ask me by any time. I'm there to reply. Okay, if any concept you can understand, definitely I'll explain. Okay, yes. Now we can move into the anomalous properties of lithium. See, everywhere in every group in the periodic table, the first element, no, it will behave something significantly from the rest of the others in the periodic table. So if you're just taking lithium or beryllium or boron, every element, no, it will actually behave somewhat differently. Why? In the sense, you know, always the leader, there is one head or the leader or boss, whoever it might be, they'll be always behave differently from the rest of the members. So that's how this will also react. So first one is, the reason is, first foremost, the kind of reason everyone knows due to the small size. Okay, so lithium is not present as a lithium because the nucleus will be more dominant, so it can't freely go anywhere. So that's why due to the small size, what happens, it shows the anomalous property. And high polarizing power, in the sense, what happens, the ionic size is very, very less, so the polarizing power will be very, very low. That is the charge by radius ratio. So what happens, the rest of the members will behave as a ionic, but this lithium will always behave as a covalent. You know the reason. The reason is, lithium can't completely transfer its electron. The lithium is having just only 3 electrons, which is present in the 2 shell. You can see the electrons are all revolving, okay, for lithium. So being very much smaller, what happens, it will not share its electron, it will not transfer its electron, it will only share. So that's why lithium will be covalent and the rest of all the elements will be ionic in nature. So this is the first. And next, Wait. Okay, next one. So, lithium will be much harder in the sense because of its crystal lattice. The arrangements is very, very close. So what happens, it will be much harder metal, and the melting point and boiling point of lithium will be very, very high compared to the rest of the all other members in the S block elements. That is in group 1. Okay, so these are all the things actually. So far you have read many reactions. Okay, so it's just a comprising point. So in lithium, it will be least reactive, but the strongest reducing agent. Why it's least reactive in the sense it can't freely donate its electron because it's under the influence of the nucleus. But the thing is actually, but it will be acts as the strongest reducing agent because of its higher hydration enthalpy. And on combustion with air, the lithium will form only the monoxide because of its small in size. And lithium is the only metal which reacts with nitrogen and forms nitrate. Rest of the metals will not react with nitrate because of its size. Okay, so the reaction will be like this. It will be like lithium and nitrogen. 2 and 2, it will be like Li6. So that's why it can sufficiently fill 2 Li3. So this will be like the reaction will be of this kind. Okay, so only lithium will be reacting with nitrogen. Okay, because of its size, it can easily go and combine with nitrogen. Rest of the elements cannot combine with the nitrogen. And lithium chloride is deliquescent and crystallizes as hydrate. Yes, because of its higher hydration enthalpy. And lithium hydrogen carbonate, as I already said, it is not at all existing in nature, which is here they have been represented as a solid form. In laboratories, it can be obtained in a liquid form, but still, the efficiency will not that much more. It is not more efficient. Okay, because it's not unstable in the sense it can't be present in the environment for too long. Okay, and next. I don't know why this is happening again and again. Yes. Okay. And another one is lithium, unlike other alkali metals, form no ethanate in the sense rest of the alkali metals will react with alkynes. Say, for example, if I'm taking here, it's not working. Wait a minute. There is some technical issues just following here. Okay, so this is the alkynes, right? So what happens here in the sense, when it is reacted with sodium, so at one part, it will be like this. Sodium. And what happens, it will be like half H2 will be released. And finally, what happens, it will be like this. This compound is sodium ethanite. And finally, this will be the final product. Okay, so likewise the lithium can't react with the alkynes. The rest of the members in S block group 1 can react with the alkynes due to the smaller size. What happens, it can't go and easily break the bond and it can fit into this reaction. Okay, so this rest sodium, potassium, rubidium, cesium can go and form their respective ethanite, but lithium can't. And see the next point, all the alkali metal nitrates, on heating, they form their respective nitrite. But lithium is the only element, it doesn't form nitrate, it forms lithium oxide, and the nitrogen dioxide will be formed. Okay, because it's just not having the efficiency to form the NO2, because NO2 is a larger anion, it can't fit into it. So that's why it simply forms the lithium oxide, and the nitrogen dioxide will be separately formed, and the oxygen gas will be released. And finally, lithium fluoride and lithium oxide are comparatively much soluble, because the reason is due to the smaller in size. Because of the crystal lattice enthalpy, what happens, their solubility will be very, very less compared to the other alkali metals. So here ends with the anomalous properties of lithium. Do you have any doubt in this? This anomalous properties is nothing but the combination of what you have been read so far. Okay, so how it is behaving, different from the rest of the members in the period S block elements in group 1. Clear?
Ma'am, could you repeat why LiF is and Li2O is less soluble in water?
Actually, this lithium fluoride and lithium oxide, what happens in the sense, they both will be having the crystal lattice. Okay, the lattice energy will be high in both these compounds. Okay, so due to that, what happens, it will be less soluble in water. The rest of the things, what happens, their crystal lattice, the arrangement will be quite weak, but here it will be very, very strong. So that's the reason it will be less soluble in water compared to the other alkali metals. Okay, always the solubility will be depends upon the lattice energy and the size. Clear?
Okay, ma'am.
Okay. Wait a minute. Wait a minute. Wait a minute. Okay, now moving to the next slide. Okay, diagonal relationship. Is my voice audible to everyone?
Yes, ma'am.
Okay, now coming to the diagonal relationship between lithium and magnesium, as I already said in my first slide itself, in periodic table, lithium, magnesium, beryllium, aluminum, they'll be having the diagonal relationship. So the similarity is nothing but you can see the atomic radii of this lithium is 152 and the magnesium is more or less it is 160. Okay, so equally it can't be present. There will be quite, the difference will be very, very less. Just make a note on this ionic radius, this is 76 and 72. So more or less you can see the difference will be very, very less. And both lithium and magnesium are harder and lighter than the other elements. Even magnesium is also harder, okay, and it will be lighter. So you can see the diagonal relationship says both the metals will show a similar characteristic, okay. And finally what happens, the oxides, the lithium will form monoxide, right? Even magnesium will also form the monoxide, okay. So and these both the oxides and monoxides also show the less solubility because of the tightly packed crystal lattice arrangement, okay. And only lithium, magnesium both will be forming this nitrites, okay. You know the formation of the molecule, right? How this molecule formed, all those kinds of things, right? If lithium in the sense, see, it is having the +1 oxidation state, even you can take the valency. If nitrogen, you can see the valency will be +3. So you have to make a compound of this term. You know this thing, right? Yes,
Yes,
or
ma'am.
no? Okay. So similarly, it applies for magnesium nitride also. And yes, both the lithium and magnesium, what happens with oxygen? What happens? They actually, this point, no excess oxygen to give any superoxides. The thing is actually, at some rare cases, what happens? Have you heard about the word elevated temperature? Elevated temperature in the sense we can adjust the temperature. Okay, I think this is not in your syllabus, but at some rare cases they form superoxides, but not in any the laboratory preparations. Okay, just information. So this oxides and hydroxides, what happen? They do not react with excess oxygen. They have trying to say both the peroxides, lithium oxide and magnesium oxide, they won't give superoxide, they will only give peroxide. And second one is, we already know this lithium carbonate and the magnesium carbonate, everything is being small in size. When you're just showing in front, when you're just giving a slight amount of heat, it will easily thermally decompose. Okay, so similar thing applies for magnesium also. That's why it shows the diagonal relationship. And both lithium and magnesium chlorides, that is their halides, will be soluble in ethanol, as I already said, because of its hydration enthalpy. And finally, last point is, they are deliquescent. This hydrated salts, because lithium having higher hydration energy, and here beryllium and magnesium both will be having the hydration energy, but comparatively this lithium and magnesium hydration energy will be similar with less difference. Clear? See, these are all the things we have already studied, so that's why I'm going a little bit fast. Okay, both lithium and magnesium will be showing the similar properties in terms of how they are forming the oxides, how they are forming their hydroxides, what about their solubility, their formings of the monoxide, and their stability of carbonates, and their stability of hydrogen carbonates, their solubility of hydrates, and finally the formation of hydrated salts. So what are all the things you have studied for lithium, it will become for the magnesium with the less difference. Clear?
Yes, ma'am.
Don't complicate stuff with the diagonal relationship and everything. Just go through the reactions, which is very, very important, and go through the reactions. Like I said, with the oxygen, it forms their respective oxides: monoxide, peroxide, superoxide. Again, taking that oxide, when it is dissolved in water, what happens? The lithium will forms only their hydroxides, but sodium will form their hydroxides with the release of hydrogen peroxide, and the rubidium, cesium, potassium will form their hydroxide, and the hydrogen peroxide is released with the release of oxygen gas. All that kind of things is very, very important. So we have came to the end of the chemical and physical properties. Now we are getting into some important compounds of sodium. Okay, so here you're going to see about the four important things, that is sodium carbonate. Sodium carbonate is nothing but your washing soda, right? So that is the formula, that is nothing but sodium carbonate decahydrate. And next one, you're going to see about the sodium chloride. And finally, you're going to see about the sodium hydroxide and sodium hydrogen carbonate. So first, initially, we can get into the sodium carbonate. Okay, so here, actually, you just don't go with all these kinds of process. See, first you have to take the ammonia. You need to dissolve it with water with the presence of carbon dioxide. What forms? It forms ammonium carbonate. Okay, so this water will go and mix with this ammonia initially. So what happens? This hydrogen will come in here, right? Okay, this hydrogen will be, this H2O will be dissociated into H plus and OH minus, right? So this will be what happens. It will goes to ammonia. And what happened? All the things will combine, and finally your ammonium carbonate will be obtained. So taking this ammonium carbonate, again you are reacting with H2O and water to make it a precipitate. Okay, to remove the impurities, what happened? The three will combine and it forms the ammonium hydrogen carbonate. Okay, so finally you are taking this precipitate and again you're treating it with sodium chloride. Okay, so with this sodium chloride, what happens? As easily this ammonia will take the Cl, okay, and it will be getting out as sodium hydrogen carbonate. So this sodium hydrogen carbonate and sodium chloride will be there. Finally, what happens in the next reaction? This is the next reaction. Taking this sodium hydrogen carbonate, just on heating, okay, barely on heating itself, what happens? Wait. Okay, so this simply on heating, what happens? It's getting dissociated into sodium carbonate, which is nothing but our washing soda, and carbon dioxide gas is released and your water molecule will be, you can be filtered. Okay, so this sodium carbonate is our compounds of sodium. So the real formula of sodium carbonate is sodium carbonate decahydrate. Okay, so it will be quite a certain amount of moisture will be there. So what happens on heating, that moisture will be removed. That will be in your next slide. You can see in this slide. So what happens in this slide, you can see you're taking the sodium carbonate decahydrate, you're heating up to 375 Kelvin. So what happens in the sense, the 9 molecules of water will be removed on crystallization. So sodium carbonate monohydrate will be formed. This is monohydrate. Okay. So further, again, you're increasing the temperature, which is more than 375 Kelvin. What happened? This water molecule also getting removed and your sodium carbonate will be formed. Okay. So this will be of the white powder. So this is your washing soda, which we'll be using in our daily purpose. You know, when after adding the washing soda in your water, what happens? It will remove all the impurities from our water. Even if your water is hard water, it will make it a soft water. Okay, and the foam and froth will come later. Okay, so this is a preparation of sodium carbonate. Clear with this preparation? Guys, got clear with this preparation? Yes or no? Okay. So actually, this preparations and all you have to go through a daily basis. Okay. So there is nothing you know, like there is no tricks in learning all these kinds of preparations. So just think, just you have to remember the basic starting reactants, which is the ammonia, water, and carbon dioxide. Okay. So that is very, very important. So, and the sodium chloride you're adding now, after that, what happens? That sodium hydrogen carbonate will getting precipitated out. Okay, because of its low solubility only, it gets precipitated out in this process. So that is also very, very important. And furtherly, you're just taking this sodium hydrogen carbonate, and what happens when you're just heating, it will easily dissociate into sodium carbonate, water, and CO2. Just remember only the process and why NaCl is adding, because to get the precipitate out, and this will be having the low solubility. So what happens? The impurities will be settled down and your product Na2CO3, that is sodium carbonate, will be easily obtained, which is by filtration. So that is the process. So this is for sodium carbonate. Okay. And now next one is sodium chloride. So for sodium chloride, there is nothing called, we are technically, laboratorically, we won't prepare anything. Actually, this sodium chloride only we will obtain from the ocean, okay, from sea. How? In the sense, maximum you can see the percentage, it is 2.7 to 2.9% mass of salt is there in ocean. No. So you will take that sodium chloride and finally in brine solution, in the sense, brine is NaCl. Okay, brine solution is NaCl. There the crystallization process will be done. So after crystallization, the sodium chloride will not be present in the purest form. Definitely there will be some impurities like calcium chloride, calcium sulfate, magnesium chloride, calcium sulfate. Many impurities will be there. Okay, so with that impurities only, you will take it, and the next step is you will dissolve with the minimum amount of water. Okay, after dissolving it in the minimum amount of water, what happens? Your impurities will be getting filtered. See, you will dissolve it with the minimum amount of waters, so you will remove the impurities. To obtain the purest hydrogen, to obtain the purest sodium chloride, what you will do? You will pass the hydrogen chloride gas. So once passing the hydrogen chloride gas, what happens in the sense? The rest of the impurities like calcium sulfate or magnesium chloride will be more soluble than sodium chloride. So what happens if it is more soluble in the sense? So they will be soluble in the water, and the NaCl, the crude crystals will be there. So easily you can remove and it will be getting filtrated out, and your pure NaCl crystals will be obtained from that process. So there is nothing called, there is no reactions in it. So simply washing it and finally passing the hydrogen chloride gas is very, very important. Because of the more solubility of the rest of the impurities, this sodium chloride you can easily gained via the filtration process. Okay, clear with the sodium chloride. And the uses is, it's a table salt, and in preparations of the rest of the compounds of sodium is also it's obtained. Clear?
Yes, ma'am.
Okay, I think this is too boring for you. I'll stop the session today. I'll continue the sodium hydroxide and sodium hydrogen carbonate. There is only 4 more slides is there to complete alkali metals. So I'll complete with this part. And tomorrow I'll go for, there is only 5 to 10 minutes will be there. And tomorrow I'll go for the alkaline earth metals. Can you please ask any doubt? If there is any doubt, please rise here. We have discussed so far about around 36 slides. No, for 40 slides we have concluded. Is there any doubts? Anyone?
No, ma'am.
Seriously? Well, I think you peoples are all under the second category, I think so. The one who got everything will have no doubts. The one who got nothing will also have no doubts. Seriously. Oh my God. Okay, you can write my WhatsApp number. If you have any doubt, you please ask me. If you like, don't hesitate, okay? So I'll write it here. This is my number. 9791978965. Okay, so feel free to ask the doubt. So definitely I'll reply within half an hour to 1 hour. Okay, so I'm managing a toddler, so definitely I'll reply your doubts. Okay. So shall we end the session?
Okay, ma'am.
Okay. Before ending the session, can anyone say about the stability of alkali metal carbonates? What is the trend which will be followed? Anyone?
Ma'am, it decreases down the group.
The stability of alkali metal carbonates decreases down the group. Decreases or increases, man? If you're just taking the lithium carbonate, it will easily decomposes on heating, right? So what happens? It will decreases or increases?
Sorry, ma'am, it will increase.
It will increase, right? Okay, so just go through the if you have your NCERT syllabus, just go through it, and if you have any doubt, please ask me. Okay, so please don't hesitate, or please don't be reluctant to ask doubts. So thank you so much for watching. Tomorrow
Ma'am, you got muted.
so come with more number of doubts. Okay, in P block also the subject will be going only like this. Okay, So just go and study all the preparations. Thank you so much for spending 2 hours and sparing 2 hours. Thank you so much, students.
Thank you, ma'am.
Thank you.
Thank you.
Thank you.